Entropy has often been described as a measurement disorder. However, in recent years, there has been an effort to move away from this perception of entropy. So the question before us in this video is, what is entropy really, and how does it actually relate to disorder? In classical thermodynamics, entropy is a measure of the amount of energy which is unavailable to do work. So classically, entropy has its roots in heat flow and work. The concept has its origins in the fact that you can only get so much work out of an engine. Here is the classical formula for entropy. S equals entropy, Q equals the heat content of the system, and T equals temperature. The first thing you may think is, so what does this have to do with disorder? The answer is that by itself it doesn't have anything to do with disorder because it's just about the availability of energy. However, this is just a classical thermodynamics view of entropy. It is just looking at the surface of what is really going on. Here is the formula for statistical entropy, where S is entropy, K is the Boltzmann constant, and P is the probability of the system being in a given microstate. Now, when the probability of all the microstates are the same, the formula reduces to this, where omega is the number of possible equivalent microstates. Now, the list of all Pi for a system precisely describes the randomness of that system. As a result, entropy can be considered a measurement of the randomness of a system. Statistical entropy usually relates to quantum mechanics as being applied to the superposition of atoms in their positions. However, quantum mechanics adds an additional layer of entropy resulting from the quantum states of the atoms themselves. In this case, the probabilities in the formula for statistical entropy are the probabilities of each quantum state occurring. In quantum mechanics, there is an additional layer of entropy resulting from mixed states as opposed to pure states, called von Neumann entropy, which is based on this formula where ρ is the density matrix and Tr is the sum from top to bottom diagonal of the density matrix. This results in the following formula, where lambda I is the probability of each of the mixed states. This results in the following formula, where lambda I is the probability of each of the mixed states. Adding Boltzmann's constant to this formula makes the units right for thermodynamic entropy, such that you get this formula. So there is no question that entropy qualifies as a measurement of the randomness of a system. So how does this relate to disorder, you may ask? The connection is that disordered systems are more random than ordered systems. The result is that a disordered system has a higher entropy than an equivalent size organized system. So is entropy a measurement of disorder? Well, not quite. But it is a measurement of randomness, which is a related and similar concept. Calling entropy a measurement of disorder is more a matter of being imprecise rather than being wrong. It would be far more precise to call it a measurement of the randomness of a system. Entropy is related to disorder, but it is more precise to call it a measurement of randomness. If you like this video, please press the subscribe button to subscribe to this channel, and also give it a thumbs up. You can also support this channel with a donation by using the link in the description.